Okay, welcome to our final lesson in visual calculus. We're going to start by completing the example that we talked about at the end of the last lesson. We're going to find farthest to the right, farthest to the left, and farthest from origin. So I've included the same diagram that we had at the end of the last lesson, plus the initial condition, x of 0 equals negative 20. And remember, we're going to do three things. We're going to identify the points where the velocity is 0, where the particle is at rest. We're going to refine that by making sure that the velocity is actually changing sign. And then we're going to be sure to include the endpoints among our candidates. Once we've evaluated our candidates, then we'll pick the winners. So, where is the velocity 0? It's 0 here. It's 0 here, and it's 0 here. It doesn't change sign, however, here, so this is not among our candidates. We have to add to that the endpoints, 0 and 9. And so we're going to build a table of candidates and evaluate the position for each of them. Well, at x equals 0, it's going to be negative 20. What about at x equals 3? Well, we're moving from 0 to 3. We need to add the signed area from 0 to 3. And what have we got? Thank you, trapezoid rule. 1/2 of 3 plus 2 times 20. That looks like 50. Okay, trapezoid rule again. Let's just continue, because what we would need to do here is say negative 20 plus 50 equals 30. And now let's go on. 3 to 6, another trapezoid rule. So we're going to go 1/2 3 plus 1 times negative 20. That's going to be negative 40. That was 50. And so at 6, we're at 30 minus 40. We're at negative 10. Now we've got to go from 6 to 8. And we've got a triangle here, 1/2, 2 times 20 is itself 20. So to get to 9, we start with negative 10, we add 20, but we also have to add this final triangle, 1/2, 1 times 10. So that signed area here is 5. That is 15. Okay, we've evaluated all the candidates, including the endpoints. Now we just pick off the answers. When are we farthest to the right? This is our farthest to the right point. Now, it's important that we are careful in understanding what a situation asks for. Are they asking for when are we farthest to the right, which would be at t equals 3, or how far to the right are we when we are farthest to the right? X of 3 equals 30. Farthest to the left. Farthest to the left is going to be, look at that, the dark horse candidate. It was an endpoint. At t equals 0, x of 0 equals negative 20. So see, if we hadn't included the endpoints, we would have not gotten the correct answer. Let that be a lesson. And then farthest from origin, we're comparing the 30 with the negative 20, and farthest from origin is going to be 30. That's it. Here at the end, I'd like to update some of the notation that we're using. I think we pretty much understand this diagram now, and it will continue to be at the heart of what calculus is about. But we're going to add a notation that is more like what you will see in your regular calculus course. So the first thing we're going to do is let's take the slope of b in the case of where it's position. Okay, what are we saying here? We're saying that the slope of the position curve gives the height of the velocity curve. Now, we're not going to teach any new math here, but we're going to use slightly different notation for this. Here's what we're going to write. Again, no new concept. This simply says the slope of the position curve at b, at time t equals b, is the height of the velocity curve. Now, there's another piece of notation we're going to use. That's the signed area. Let me show you the calculus notation for signed area. So again, signed area a to b of the velocity curve, for example. We're going to now write that as follows. Again, no new concept, and no need to be intimidated by what is obviously an unfamiliar symbol for those that are just starting off into calculus. But it means the very same thing. The signed area of the velocity versus time curve from t equals a to t equals b. So now let's rewrite what we've got here. So our diagram is going to be changed now. We're going to rewrite this as slope of the position curve at t equals b. We'll rewrite this as slope of the velocity curve at t equals b. And we can rewrite this as well. We're just going to write position at t equals a plus the signed area from a to b underneath the velocity curve. This one, similarly, the velocity at a plus the signed area from a to b of the acceleration curve. That's it. Again, this makes calculus textbooks a little bit more accessible to you. Now, these symbols will come to have a much deeper meaning. I'm not trying to minimize that. There's more to learn. But for now, there's no reason that you can't start to get comfortable with the symbols of calculus, even though they have the limited meaning that we've given them so far. We've come a long way since we first headed out from Annapolis down to my grandmother's house in Virginia Beach. And hopefully you've learned quite a bit to give you a framework for what your college calculus or AP calculus course is going to be like. A lot of your understanding is contained in this diagram, which has continued to evolve and become richer. But let's just recap a few of the things that we've learned. Initially, we started out with simply the d equals rt equation. But we learned that we could make a d versus t diagram and find the r hidden in the slope. Conversely, we learned that we could make an r versus t diagram and find the d hidden in the signed area. That led us to constructing our first version of the basic diagram that connected d versus t and r versus t via slope and the area. We learned pretty quickly that until we add the initial position in, we are not accurately reflecting the situation. And so it's not a perfectly symmetric situation between d versus t and r versus t. We simply cannot forget the initial position. Next, we saw how, by defining acceleration, we could extend the diagram to cover acceleration, velocity, and position. We went on to refine our understanding of signed area and the fact that it's different depending on the direction in which you compute it. That allowed us in turn to be able to compute curves moving both backwards and forwards in time. And so we understood that the initial condition, whether that's position or velocity, really isn't about the position or velocity at time t equals 0, but it's simply about any time where you initially begin to create your graph. We talked about speed as the absolute value of velocity and showed that once we had the concept of speed in hand, we could make careful distinctions between such things as total distance traveled versus change in position versus final position. We also realized the need to read used car warranties very carefully. We talked about minimum and maximum and how we find both candidates to calculate extrema and then evaluate those candidates. And for good measure, we even threw in a little rocket science. Well, I hope you've enjoyed learning as much as I enjoy teaching, and I wish you the best in your college or AP Calculus course. Feel free to write me if you have recommendations, criticisms, suggestions for improvement, or if you just tell me that it helped. I look forward to hearing from you, and good luck in calculus.